Let us now discuss how to go about simulating a full wave rectifier with capacitor filter. Recall that some time ago, earlier, we had discussed this circuit, the full bridge rectifier circuit having the 4 diodes in a bridge configuration, the capacitor and the load. And we are also familiar with the output voltage wave shape and also the current that flows through the various branches of the circuit. So let us put them into KiCad schematic and then simulate the circuit in ngSpice and see how to get the results. I will now click on the KiCad application and open KiCad. It is showing the previous project which we did of a rectifier circuit. Let me open a new project. And I will call that one as, let me open a new project as full wave rectifier project. So a new project is created. You can see that, we can see in the file browser that a new project here is created with new files. So we will use that full wave rectifier and open the schematic. So let us open the schematic, and first let us give a title heading here, full wave rectifier with capacitor filter. So this is our title. Let us place it somewhere here, and then now let us draw the circuit. So the circuit is exactly same as this. Let us put this together. We'll take a source, we'll take in 4 diodes, capacitor, resistance, and then also probably to measure the currents we will place 0 value voltage sources at these positions. So let me take this icon here, add symbols icon, and so in the schematic on the right side, as before, let me pick this icon, add symbol icon. I will click that, and we will get the symbol elements. So let me pick the V source, the sine source, V sine source. Let me pick that. I'll just place it here, and then we will need diodes. I'll pick the default diode, and let me place 1, 2, 3, 4th one also. So I have the diode, then the capacitance. Let me take the generic capacitance, then let me also take a generic resistance to act as the load, and we have the load here. So we have the components here. Let me also pick the current measurement. Okay, I can copy it from here. So let me change the cursor. So I will copy this and I will paste 1, 2 and 3 current source values, which I will make it 0. So this will be our input source, and let me rotate and then place the diodes here. Rotate this, each one of them. D3, so like that we will make the circuit for the bridge, and then I will also make the current source measurement sources here, make it available. I will rotate them and keep it appropriately here. The plus sign, remember the plus sign, the current should flow into the plus sign. The normal conventional current flows into the plus sign of the source, and have it. And we have this load, and I will connect the load here. Okay. So let me first double click on this current source, and I will kind of hide them so that it's not visible. And here I will make the amplitude 0, frequency also I will make it 0, so that these are something that I want to, I will copy that, right, and then OK. So this I will bring it in, then I will double click on this. I will see that this is not displayed. I will hide this also, and what I had copied I will paste it here. 0 DC, 0 amplitude, 0 frequency. And I will move this a bit here. Likewise for this current measurement point also, I will hide this and paste that. So 0 DC, 0 amplitude, 0 frequency. So these are the current sources which will measure the currents in this branch, this branch, this branch. And now let us make the interconnections of this. Now this is the input source, which will be 325 volts peak, 50 hertz, and that is your input sine source. Now on the right side, I will take the wire icon, add wire, and use that to make the interconnections. So I will connect these two here like this. Let me adjust this such that they are in line. Then I will make the connection here, this fashion. Just follow the circuit diagram that we have seen for a full bridge rectifier circuit with capacitor filter. So this is the circuit. Let us connect the input source to the center of the bridge in this fashion. So you see that the circuit is more or less complete. I need to add the reference node. Remember that SPICE needs a reference node, a 0 node, which is the reference node with respect to which all the voltages are calculated. So do not forget to add the reference node. So let me take this as the reference node. That is the 0 node. that way. So let me position it like that. So this is the first step, drawing the circuit. Next, we need to give some values. These are all 0, 0, 0 voltage sources. This is 325 volts peak sine wave. Values for the capacitance. So let us say that I give 1000 microfarads. I can give here 100 ohms. So we see that we also have the values here. The next step is what, after the netlist is generated, what should ngSpice do? So we need to give some control commands to indicate to ngSpice what type of analysis that it needs to perform. So we want to perform transient analysis. So let us include this transient analysis part here as a text element. So control statement and dot end control statement dot nc. So within that one you can include the transient analysis that it has to do, 1 microsecond, 100 millisecond, use initial conditions. So this is the transient analysis that we want to do with 100 milliseconds, that is 5 cycles to be displayed. So let me run that analysis. I can here at this point also, like last time, set the color of the foreground, of the background, color 0, background as white. This means, let me give some comment, set background color to white. Then set color of the foreground to black, which statement is basically set foreground color to black. Then we need to plot. So what do we plot? So let me just leave that blank at the moment, because I need to assign the, I will place it here for the moment and pick this icon, place labels, add labels. So let me pick this. Let's say I will add label A. So this label A, let me add one here, and then let me add B. I'll add B here. I will add one more here. I'll say I'll call that C. I'll say this is C, and I will add one more node here, and I will call that output node O. So this will be O. So let me connect them with the wires. So this is connected to this point. This is connected to this point. C is connected to this node. The output node is connected here. So now all the nodes that we want are defined, well defined. Therefore I can give plot voltage A comma B for the input and the output voltage. I want to see the output voltage. Let me do left justification, and yes. So we have the control commands that will get executed once you get into ngSpice. Now this is something that we need to save. So let us save the schematic as a .cir file. Then export netlist, spice netlist, export. So into full wave, into that folder, full wave rect folder, full wave rect.cir, save that one. So when you open the full wave rect.cir circuit, let us open that. The full wave rectifier.cir file appears like this. So this is the part here what I am marking, which are the control commands which we have written in this text box in this schematic, and this part is nothing but the circuit. There is nothing but the circuit with the component and the node name and the value. So this is what is the net list of the circuit part. And the diodes that we have used, the default diode models as provided by SPICE. So that's what we have used. Now let us simulate this and see what are the various waveforms. For this, let me open a command window and let us call ngSpice to use the full wave rectifier.cir file. So you see that, so we'll execute the simulation, and you see what is plotted is what we have asked it to. VAB, the input waveform, which is red, and V0, which is the output waveform, the one with the ripple. You can also see the current waveforms. So let me plot the current waveform and then see how the current waveform looks like. Plot I. So which voltage source shall we see? So if you see, we have V2, V4 and V3. Probably we can see all three. So plot V2, plot I of V3, plot I of V4. So you see, this is the first cycle where the capacitor is not charged and you see a very large current. Then followed by other subsequent cycles where capacitor, as it is charged, the amplitude levels of the currents are smaller. And the blue waveform is IV3, which is output DC going to the load, and there is this orange waveform I4, which goes only through the capacitor, and it has a zero average. What you can expand by marking. So let's say I expand this much and then see. So I can expand that and then see the various currents. So this is, let me move this away. The one that is flowing through the load is IV3. So IV3 is the blue waveform flowing through the load. The red one is what is coming here. What is coming here, IV2. And going through the capacitance is the orange colored waveform, which goes plus and minus such that the charge is balanced. The current through it, the average current is zero. So this is the waveforms that you can see, and then you can probably check various other voltage and branch currents. I can do an alter. I can change the value of C here to the one which we had used during the half-wave rectification, 100 microfarad, and see comparatively what is the ripple. So let's say that, let me do a listing. This is the listing, and let us change the value of C1 to 100 microfarads. So alter C1 value to 100 microfarads and then do a tran 1 microseconds to 100 milliseconds UIC. So that being done, the analysis being done, I can plot VA comma B, the input voltage, and V naught to see that this is the output ripple in the case of a full bridge rectifier. In the case of the half wave rectifier, we saw that this blue ripple traveled up to this point till it intersected the next positive rising. But here you see that because the full wave rectification, the bottom portion of this is rectified, and because of that you see that the ripple frequency is double and also the ripple is lesser for the same output C and R. So what I have done here is downloaded the data sheet of a popular diode, the 1N400X series, so that we can find what is a suitable diode to be, practical diode to be used here. So the diodes that we have used here are generic diodes, default diodes. What would happen if I am using the diodes that we are supposed to practically use? So if you take the 1N400X series, so you have 4001, 4002, 3, 4, 5, 6, 7 like this. So you see there is some change in the ratings. You have a 50 volt rating, 100 volt rating, 403 is 200 volt rating, 4004 is 400 volt rating, so on, voltage rating. So you have to, when you are practically using, you won't be using any default diode, you have to go and pick from commercially available lists to pick a diode which will be appropriate for the rating that your application demands. It has a 1 amp average forward current, and let us say that we want to use one of these. Remember that in our case we are giving the input voltage coming from the mains grid, which is 230 volts RMS, which is 325 volts peak. So the diode should at least withstand the peak voltage of 325. So let us say that even with some tolerance, we can pick either 4004 or 4005, which is 600 volts. So let us say that I will pick 4004. How do you incorporate them? How do you incorporate this diode model into SPICE? So the models are not directly given in KiCad. You will have to either go to the manufacturer's site, or you can go onto the internet and try to find the PSpice model of a specific device. So let's say that let me go to the browser and search, and I've searched here and put 1N4004 SPICE model. So you will probably find SPICE models from given by the company manufacturing it. So there is a SPICE model here. Probably if I click on that, so I will get the SPICE model, so it gets downloaded. So let me open that. Here. So this is the SPICE model of 1N4004. 1N4004. So let us use this model. So in the default diode, if you look at the full wave rectifier, the default is just D. So D within brackets, if I use all these parameters, are given by the technology that is used to make these diodes, we will have slightly realistic model, which we will have a diode which is slightly more closer to reality than the generic models. So how do we incorporate them? So one way is that I can copy this and paste it here. I can copy this and paste it here like this, and use the same model for all the devices. So this way you have 1N4004 model incorporated. It's a 400 volt breakover voltage incorporated. So let me save this .cir file, okay, and execute the simulation, which means let me go back here. I will exit from the ngSpice. ngSpice.cir. So you have this. You don't actually see much difference here, but I would like to see what happens if I exceed 400 volts, if the input exceeds 400 volts. You see the diode voltage. I will also plot the diode voltage. Plot diode voltage is between A and this node is nothing but C. So between A and C. So let us say between A and C, what do you see? Plot voltage A comma C. So this is the diode reverse voltage. See, that goes up to 325. Now what would happen if I say that the input voltage waveform has crossed 400 volts? Okay. The input voltage crosses 400 volts. That should get reflected here, isn't it? That should get reflected. So let's say this becomes 400. And in the circuit file, I will not change it here. What I will do, I will go to the circuit file. V1. What was 325, I will make it, let's say 500. So I now have an input sine wave of 500 volts. See that I am only now operating in the .cir. I am not even going back to the schematic. I can just change in the .cir and then re-execute the .cir file. So let us say that I exit and re-execute. So when I re-execute, you see that because it has crossed the 400 volt rating, the breakover has happened, and then the simulation will not behave in the manner it is supposed to behave. So you see that the simulation has also not gone through the whole extent. It has gone now, instead of going to 100 millisecond, it has stopped at 5 milliseconds. So whenever you have simulation that is aborted, you can expect that there is some issue with the circuit. So one way that you can try to proceed with the same things in the simulation is to include a dot option statement. So let me include a dot option statement here in the control segment. So again I am modifying only in the .cir file. So .cir file modification is like a scratch pad. You can quickly, the turnaround time in making changes and seeing the results can be very quick. So I will use a dot option. The dot option, the relative tolerance, rel tol, I will set it at 0.01 resolution. The absolute tolerance, ABS tall, also I will set it at 0.01, and the voltage tolerance at 0.01. So let us say, so many a times you will see that by setting the relative tolerance, absolute tolerance and the voltage tolerances in the dot option, your numerical issues can get sorted out. So let us save this and rerun the simulation. Then let me go back to the ngSpice. I will exit it and once again call ngSpice full wave rectifier, the modified.cir file. So you see that the execution is now full time, full 100 milliseconds, because the tolerance has played a role in trying to solve the numerical instability issues. But you see that you are not comfortable. You can see that there is a flattening of the voltage that happens beyond 400 volts because the diode that you have chosen is having a breakover voltage of 400. So when you see a waveform like this, you should immediately suspect that there is something wrong and that I have chosen a wrong device. So you go back and change the device ratings. So this way you can kind of iterate to kind of choose the ratings of the devices properly. So if I go back to the CIR file, if I go back again to the CIR file, I remove this. I make a default ratings. I make the diodes back again to default diodes. I remove the 1N4004 diode model. So now they are back to generic diodes, which means that there will not be any issue with the ratings. You should get proper waveforms. You can check that out. You can see that. You can check that out. I have saved it, and then I will go back to the command line. I will exit ngSpice and rerun the ngSpice using the updated .cir file. Now you see that because I have used the default generic diode, again rating is not an issue. It is able to give you the correct waveform even at 500 volts input sine wave. Whenever we wanted to change the model of the diode, we saw that we go to the .cir file and edit the model of the diode here, and that's what we did. And then we showed you how to incorporate the diode model of a practical 1N4004 diode, the SPICE model. But this is okay for quickly trying out the things, but in the long run, when you want to do it from the schematic, then it is good to see that you incorporate the diode models at the schematic level. How do we do that? So if I double click here, you will see that at the bottom there is a button in KiCad called the simulation model. So when I click on the simulation model, see that there is this radio button which is clicked, built-in SPICE model. But I don't want to use this built-in SPICE model. I don't want to use the generic model given by SPICE. I would like to use my own model. So click this SPICE model from a file. So whenever you get models, you can collate them, you can put them into a file, call it as .lib file, and then call it here. Okay, so let us create this .lib file first. So in the text editor, let me open a fresh file here, new document, and here I will copy and paste the SPICE model. I will make a command line, SPICE models for diodes. So So let us say that you have a file dedicated for spice models of diodes, and all the spice models that you get are built over a period of time. You start putting in this particular file. So we just saw from the net, we downloaded that this is the spice model for the diode 1N4004. Okay, I will copy that and go to this file which I just created, and I will paste that, and I will give it a name, dot model D1N4004 and the spice model. I'll put in the spice model like this. So this is the spice model of this particular diode. So now you save this. So let me save this. I will save it in the same directory, which is full wave rectifier. I will name it as diode models .lib. Name it as diode models .lib. Save. So now that is done, right? So that is done. So here, when you go and double click on the component, I'll double click on the component and go to simulation model, spice model, and here I'm going to browse and pick diode models. This is what I just now created. Pick diode models, open. So diode models are selected. So when I go into the model list, see the list of models, there is only one model which we had typed in, which is D1N4004, that shows up. Take that, choose that. Okay. Here on the top, you see pin assignments. There's a model on the left which is selected, pin assignments. If you go to the pin assignments, you will see the association of the pins in the symbol and the pins of the model that you have downloaded. So the model pin assignment is like this. Pin 1 is assigned to anode, pin 2 is assigned to cathode. In the symbol that we have used in KiCad, apparently pin 1 is given to cathode and pin 2 represents anode. So we have to correct this. You have to always see that the symbol pins and the model pins match. So I will go out, cancel this, and then choose another thing. That same dialog box, look at this edit symbol. You click on this edit symbol and the symbol editor appears here. Okay, so the symbol editor appears. It will appear in this fashion. You may have to disengage all this. Now here, these are the two pins. Now if you look at, this is the anode, and this anode is assigned pin number 2. Make it pin number 1 because the model demands that anode is pin 1. And this is pin which is cathode, make that pin 2. So now your pin assignments are fine. You can save that and close this. And here in this diode model, now you click on that simulation, pick the file, the diode model lib file, open it, choose diode model, and now you see the pin assignments. 1 is anode, 1 is anode, 2 is cathode, no problem. So you should be able to go forward. So you can say OK, and I can use the same model, copy of it for all this. So what I will do is, instead of doing it for all the 4 diodes, I will delete this. And because I have already done it properly for this, I can copy and I will place it here, paste. I will paste another one here, and I will paste another one here, so that I have now 4 diodes with the same. So if I take, for example, diode 4, you will see that the model is like this, what we had downloaded. Okay. So now that I have practical model there, can use that. I will also go into the controls. Remember that I had included the dot options statement, right? So here I will include the option statement. Option relative tolerance equals 0.01, absolute tolerance equals 0.01, voltage tolerance 0.01, so that I also have that line put in there. Okay, so that will now appear here. So now you have a circuit where the component, the diodes, are based on practical models D1 and 4004. So this I can save this, and I can export the netlist, SPICE netlist, and export it into full wave rectifier.cir. So let me save that. So now that is saved, and I should be able to see the changes here. Now what are the changes that you are going to see? One thing is there is an include file. So you see that it will generate the path. You are given this, you browsed and picked this diode models.lib file, which contains what? It contains this library which we created. Let me now go to the command window, clear the command screen, and execute ngspice rectifier.cir. So you will see that the waveform, of course, is as expected. You can see the listing. So in the listing, see that what is being simulated is the one with the model D1 and 4004. The model has been taken from this library and included into the ngSpice environment for simulation purpose. So this way you can introduce your own part model, SPICE model, even if it is a newer one, or if you get directly the SPICE model from the manufacturer, you can incorporate it in this way. If you wish to make any changes in the parameters, like for example parameters of the sine wave, the amplitude which is 350, you want to make it 500, then it is better you do the changes in the schematic. You can do the changes in the .cir file that, like I showed you before, to make any quick changes, to do quick tests and have a quick turnaround time in testing out your system. But for documentation purposes and for more clarity in the entire process, it is better that you do it at the source file, which is your schematic source. Go to the schematic, make the change here. Let's say you want to make it 500, right? And then save and re-export the netlist. Export the netlist, save it as a .cir file, and you will see that it will reflect in the .cir file as 500. This you can simulate and do all your changes. If you probably simulate this, the 1 and 4004 model is rated for 400 volts, and therefore you will see a clipping action happening. So for example, let us go back to the command window. Let me ngspice full wave rectifier.car and let us simulate, and you will see that at 400 the diode clamps, and you should understand that there is a problem with the diode rating. Therefore it will caution you and prompt you to look back into the design and recheck on the device or the component that you have chosen. So this is how you kind of iterate to make the design, to use the simulation and the design process in order to get a better circuit with proper component ratings.